So our first speaker today is Ian. So Ian has been a student with our group since at least 2017, and he'll be talking about, I think, vector self-interacting dark matter.
No, I'm going to talk about the continuum-mediated self-interacting
good,
dark matter.
even better. Okay, so you can go ahead and share screen.
Okay, I think everyone should be able to see that, right? There we go. Can everyone see that? Okay. Oh no, oh no. It's doing the, sorry, give me a second. It's doing the, it wants to, I put it on slideshow, full screen should be better. Okay, sorry. Okay, so this is a project I've been working on with my advisor Flip and Sylvain Pichette. I probably should put his institution on there. But this project, it's continuum-mediated self-interacting dark matter. So it's basically exploring the self-interactions of a dark matter model with a 5D mediator. So at this point, I think everyone in this audience is pretty familiar with what dark matter is, and that much of the research now has turned to dark sectors. Particularly, I spent a lot of time researching dark matter with a light mediator, and in these scenarios, the dark matter doesn't interact directly with the standard model as like a lot of WIMP models had, but it interacts with the standard model through a light mediator. So generally, in a simple dark sector, there's like one or maybe a small number of light mediators. And we can have things like dark matter annihilating into pairs of mediators, or we can have dark matter self-interactions, which we're particularly interested in. So with a 5D mediator, we consider what's been called a warped dark sector. And this dark sector is basically described by a slice of ADS5. And we consider the dark matter to be a brane localized field, and it interacts with itself and possibly the standard model through a 5D bulk mediator. And in this model, the interactions are mediated by many KK modes. So the geometry for this is like pretty similar to Randall syndrome 1, where we have two branes, but in Randall syndrome 1, the standard model is generally on the infrared brane. And like there's some UV physics on the UV brane, and they're more interested in the warping effect of things like the Higgs web and stuff like that. And we're not so interested in that. We just care about the mediator, the phenomenology from the 5D mediator. So why do we care about self-interacting dark matter particularly? Well, dark matter self-interactions, as many of us know, can thermalize galactic inner halos, and that reduces the central density. So reducing the central density can alleviate things like the core cusp problem, where we observe more cord-like galaxies, but simulations give like a cuspier profile that peaks in the center. And this can all be connected to the scattering rate. And since the velocity distribution of dark matter and the density distribution are roughly known, the main quantity of interest is the cross-section divided by the mass. So this is Hypo's work. What spectrum do you need to actually agree with astrophysical data? So you can come up with like a phenomenological model of a spin 1 mediator. And if for some reason there's an asymmetry in the abundance, so you have only a repulsive UCAL potential for the low energy interactions, then you can satisfy the data with a 15 GeV dark matter particle and like a 17 MeV mediator, and coupling that matches the fine structure constant, the ENM1. But the dark matter mass for symmetric freeze out's been constrained to be sub MeV, or sub GeV. So that's not ideal. So what we consider is like a quasi-conformal sector. So it's a slice of ADS5 with this metric. And essentially on the UV brane, you can consider like the elementary states. And on the IR brane would be like more composite states. But what we actually consider is this warped dark sector. So on the UV brane, we are like visible states. the dark matter can either be on the UV brane or IR brane. So I don't want to say it's technically visible, like it can be, the coupling could suppress how visible it is, but there's a reason why that I'll get to why we can't see things on the IR brane. And the mediators, the KK scale, which is the scale of the mediators, is set by the scale of the IR brane, which is mu. So the KK scale is about pi mu. And in general, we assume that mu is much less than K, which is the scale of the 5D curvature and the UV brane. So a bulk 5D mediator has an action like this. And the brane Lagrangian determines the boundary conditions, which can determine if there's like a zero mode or a light mode in the spectrum. So you generally proceed with like the standard Kluser-Klein decomposition, and the propagator can be expressed as the sum over 40 propagators weighted by bulk profiles. And the bulk profiles can be found from the equation of motion, and they're given by Bessel functions, but they're indexed by this bulk mass parameter alpha, and that alpha is related to the conformal scaling dimension by this equation here. And since this is a Sturm-Liouville problem, it turns out you can normalize them too. So while that's useful, but what we really are interested in for our study here is the mixed position momentum space propagator. So you can solve the equations of motion with a delta function source, and there's various methods. Method of variations works, or you can just break up the regions. It's a few ways to do this, but you end up with this mess of Bessel functions and stuff. And these tilde functions are determined by the boundary conditions which come from that brane Lagrangian. And for the case of BUV and BIR, defined here being 0, you actually end up with a massless mode in the spectrum. And that we don't want a massless mode in the spectrum for the purposes of SIDM. So one thing I've also not mentioned is that you can also have brane localized kinetic terms. So these become important when alpha equals 1. Otherwise, they're subleading in the propagator, and we can just ignore them. But when alpha equals 1, they're relevant and they affect the boundary conditions. And we only consider a UV localized one because that's all we need. But in principle, there could be IR and UV localized terms. But they essentially just control the localization of a bulk field. So if you were to make C very large, then you would have approximately a field localized on UV brane. Okay. So the spectrum of Kluser-Klein modes you get from the propagator is just given by the denominator, and it depends on whether whether BUV is 0 or not, what you get for the N1 or greater modes. And for this, we consider BUV equals 0 because of the specific potential it gives us. That's the case we're interested in. And then for P less than mu, or for momentum less than mu, you get a 40, what looks like a 40 mode that's lighter than the scale mu. And you can see from the mass given there that if you actually take BIR to 0, you get a massless mode. And we'd already taken BUV to 0. Okay. So one of the last things we also need to consider is bulk self-interactions. So if you have bulk self-interactions, it induces imaginary part to the propagator from the self-energy. And what that does is shift the poles of the propagator off of the real axis. And we'll see in the next slides that effectively smears the KK modes into a continuum, among other effects. So that brings us to the warp down cutoff and the transition scale between the continuum regime, what we call the continuum, or what is called the continuum regime, and the KK regime. So there's a cutoff for the 5D theory given by just like the spacing from the metric, and that's 1 over lambda. So if you relate that to the 40 momentum, then you get this warp down cutoff at some position Z. So when the momentum is higher than that, the EFT begins to break down on the IR brane. If you have a fixed P, once you get to the IR brane, it breaks down. So that implies that there's the existence of this transition scale, lambda tilde, related to capital lambda times mu over k. And beyond this scale, the IR brane is essentially removed from the theory, and this is called opacity. So it essentially censors the region of the theory which we don't want propagation. Like, you don't want things to reach the IR brane, and it naturally does that through these considerations. So in these two regimes, so for p less than lambda tilde, if you have a small enough forward momentum, the narrow width approximation is good, and you can still have KK modes mediate your interactions. However, near the transition scale, the widths start to matter, and the modes start to spread out, and you have what looks more like a continuum. And then above the scale, the bulk self interactions have this merges into a continuum, and you can't consider the KK modes to be 40 asymptotic states, and that's something we'll get to later. But this is, you can see this in the propagator when you consider the bulk self interactions. So for what we consider for continuum-mediated self-interacting dark matter is essentially the setup I've been describing, and we localize the dark matter on the UV brane. The standard model may be on the UV brane also, but it's not the focus here. And there may be other states on the IR brane that we don't know about, but again, they don't affect the dark matter self-interactions. And like the kind of scales we consider for this are, for the curvature, we consider around 10 to 10 to 3 TeV. That's like different from Randall syndrome. It's like Planck scale. And then for mu, we consider from like 0.1 to 100 MeV. So that's like about the mediator scale, pi mu. So it's from 1 to 1 MeV to 1 GeV about. So the dark matter has an action like this, and it's given, or it interacts with the bulk scalar through this Yukawa-like interaction. And from naive dimensional analysis, the dark matter's coupling has a rough maximum of about 4 pi, which I think is the standard for a 4D field. And like I said before, the standard model may be on the UV brane also, but it's not particularly relevant for this, so we'll just don't consider it. So since we have dark matter on the UV brane, we care about the UV to UV propagator. So when you actually evaluate the propagator on the UV brane, one of those terms in the numerator simplifies, and you get something a little nicer. And you can expand this in the P much greater than mu, but less than K limit. And you can actually see that the poles or the masses I gave before show up in this S alpha factor. However, if you have an imaginary part, so this is why the width is important and the bulk self interactions are important. If the momentum actually has an imaginary part, then this S alpha is approximately -1 to the alpha, and the poles in this expression essentially merge into a branch cut on the real axis, the real P axis. And then for P less than mu, you have this propagator here that again looks like kind of like a 4D propagator. Okay, so for the self interactions, we want to calculate a potential. So the potential is given by this diagram here, standard T-channel diagram, and then you end up with the propagator. So if you relate that to the 4D or the momentum space potential, and then do a Fourier transform, you can calculate this potential, and it's interesting because it has a fractional power law. So it goes r to the 3 minus 2 alpha, or 1 over r to the 3 minus 2 alpha. However, for self-interacting dark matter, we want there to be a mass gap, because if there's no mass gap, when you go to low energy, the cross section just keeps blowing up, and that's not what's observed phenomenologically. It wouldn't work well with data. So we want our model to have a mass gap, and we know there's a mass gap because we took mu to be finite. It's just that in this approximation here, like where mu is too small to be seen. So we have to do a little better. So we can remember that this interaction is just the sum of Yukawa potentials, essentially, because it's you can write the propagator in the spectral form. That's a sum of 4D propagators. So you just go ahead, Fourier transform each term, and you end up with this sum of Yukawa potentials. And then what we can do is use this identity where, since the bulk profiles are essentially residues of the 4D propagator, you can relate them to a contour integral and then a discontinuity along the real axis of the propagator. So if we do that and cut the bottom limit of the integral off at the first kk mass and take the upper limit to infinity, we actually derive this potential here, which matches the other one up to when m1 goes to 0. Because this is I didn't know about these things till I derived this, but it's a regularized gamma function. So it's gamma of 2 minus, sorry, it's a regularized incomplete gamma function. So it's gamma of 2 minus 2 alpha m1 r. So it's like a gamma function, but you cut the integral off the bottom, and then it's normalized by a normal gamma function. So this plays a role of like an exponential suppression. And we can only consider alpha greater than 1/2 because below that it's a singular potential, and numerically it's not much we can do about that. But this is nice. It gives us something that agrees qualitatively more with what we'd expect. So the alpha equals 1 case is also unique, and that you get the light mode separated out from the continuum, and that's the dominant contribution. So in that case, you basically just get a standard UCAL potential with this is the residue you get from the propagator, and that's basically the same thing as ordinary SIDM, but with just a different coupling. So like, how accurate is this potential? So the fractional, we're comparing the fractional power one from a couple slides ago to just an explicit sum of KK modes. And you can see as you increase the amount of KK modes, they actually agree quite well in the small r regions. And sorry, this should be M100 and this should be M1. They got switched. So you shouldn't really go beyond here because that's like the longest range you can go. But there's more lines that just aren't included for the, the 10 to the 4th max KK mode. So like they actually agree quite well. But they do start to diverge a little bit here, but qualitatively, they do give like similar phenomenon. There's just like an order 1 difference in the potentials. However, if we go too close to 1, the potentials actually don't, or if we go too close to alpha equals 1, the potentials actually don't agree by a lot. And that's because the Bessel Y has like, you have to change the definition for it. So there's some subtlety there, and you have to rederive something else. So we just kind of, at a certain point, don't go beyond that and then jump to alpha equals 1. But if you really care, you can do a slightly more subtle expansion of the Bessel functions. Great. So for a fixed value of alpha, the phenomenology is very similar to SIDM. So you see like these regions. So this plot on the right is from one of Heibo's papers, and you can see that for smaller mu, there's like this classical scaling region. Fortunately, we don't have an analytic approximation for that, but there's a resonant region, and it agrees very well with the Born approximation for large mu. And you can see the regions here compared to the standard SIDM regions, and the classical region is defined really similarly. However, you can get this expression for the Born approximation, which seems to agree really well with the numerical results from this. You can see the dashed purple line is given by this here. So the cross section, so like for a fixed alpha, it seems to display many like of the same features as SIDM, but the cross section is like very dependent on alpha. So you can see from the figures, the left figure and the right figure. On the left, it changes by many orders of magnitude as you increase and decrease alpha. And generally, if I was to go any lower, it would just get, the cross section here would get smaller and smaller. But you can actually see like resonances too as a function of alpha. So what that means is, so these are some old fits I did. I have some better ones, but I wasn't able to make them into a nice plot. But you can see that for different values of alpha and different masses and like different couplings and stuff, you can essentially you can fit it to the roughly. So these aren't very, I'm not minimizing the fit. This is a rough fit, but you can roughly fit it to the observed data from dwarf galaxies, low surface brightness galaxies, and galaxy clusters. And this is just a comparison to like the plot I showed earlier, Heibo's plot. So it's nice that we have essentially extra parameters to move these curves around. So I haven't talked out like freeze out constraints or annihilations. So you can go ahead and calculate what annihilation into KK modes would be. However, recent work from Lexi and Flip and Sylvain they've shown that essentially, for the higher KK modes, that what happens is you end up with cascade decays, and these are phase space suppressed. And for the lower KK modes, like this F, the bulk profiles suppress interactions as well. So in their paper, they calculated decay rates, but it should apply as well to annihilation rates. So although you can annihilate into a KK mode, they're unstable and have to undergo these cascade decays, and essentially the rate is suppressed. So for this study, we have ignored annihilations. There is the possibility of like radions, so the radion mode of the graviton field, or the metric, sorry, that could be a possible decay or annihilation product, and also the lightest KK mode. However, the light mode, but the light mode is has a suppressed coupling, and again, the couplings are pretty suppressed. So we generally don't consider freeze out in this study, and that's actually something I'm working on now for a future project. But yeah, we generally assume the freeze out isn't a factor in this because of this phase space suppression and the suppression from bulk profiles. So the future directions, we don't know what the contribution to dark radiation should be. So that's something that Lexi is also working on. So hopefully we'll have an answer to that pretty soon. But I think the idea is that it's suppressed by the temperature of the bulk, and that has to do with this it being a near conformal sector. And then the other thing I'm working on with Lexi is we're working on like a more full model of dark matter in this type of setup, where we consider all the annihilations in different regimes and what possibilities there could be in that scenario. So that's all I have. So any questions?